In this video, we'll discuss Gauss theorem in electrostatics. Students, Gauss theorem is a very important theorem in electrostatics because it has given us so many formulas which otherwise perhaps would have not been derived. So, to understand Gauss theorem, we'll first understand what is electric flux. Electric flux we see that this is a surface, rectangular surface, and there is a axis kind of thing which is passing through its center. See, this is a vector actually, and this is called area vector. Now you will say area and vector. Area is a scalar quantity. Yes, area is a scalar quantity, but in electrostatics we consider it as a vector because in many places we need direction of area. So we take the perpendicular line drawn on the surface as area vector, which gives us the direction of this area. Now, how this area or area vector is related with electric flux? Suppose we have electric field at some place which is directed in a particular direction, and I'm showing it with the help of these electric field lines, parallel electric field lines in a direction. Now, if the area is placed in the path of this electric field, say like this, it's placed like this, then we can see that all electric field lines are passing through this area perpendicular to it, and the area vector is parallel to electric field line. So in this case, whatever is the number of electric field line that passes through this area, we can, if I count, suppose 1, 2, 3, 4, so 4 electric field lines are crossing through this area. So this number of electric field line which is passing through this area perpendicular to it is called electric flux. So how do we define electric flux? Electric flux is the number of electric field lines which are crossing, these electric field lines which are crossing through this area perpendicular to it, that is called electric flux. Now suppose area is not actually in this position. We change the position of area. Suppose we put it like this. Suppose now area is rotated slightly and it is put like this. Then now we see the area vector has some angle with this electric field line. Suppose that angle is theta. The area vector, this, and electric field line, this, they have angle theta. So in this case, we'll have to find the component of electric field which is perpendicular to the surface. How we do that, that we'll see, and then we'll get the formula for electric flux. Now suppose this is the area and area vector is like this. This is the angle theta between. This is area vector. So I'll take component of electric field along this direction, which will be equal to E cos theta. So electric flux, which is denoted by phi, this is product of E cos theta into the area of this surface. So E A cos theta, we can write it as E dot A dot product. So dot product of electric field and area is known as electric flux. So obviously electric flux is a scalar quantity, and its unit will be Newton meter square per coulomb. Now suppose I have an area whose magnitude of area is not known. It's not a regular surface. For example, I have taken a surface of this shape, suppose. Now this shape, I don't have a specific formula to calculate area of this shape. Then how do I calculate electric flux which is passing through this surface if there is some electric field passing through this area? Suppose we have an electric field over here like this. For this we use integration method. How do we use integration method? This is electric field. These lines are passing through it. We'll take a small portion of area. Suppose I take a rectangular or a spherical shape whose area we can calculate easily. Suppose I take this much area and its area vector is in a direction, say called dA. Then flux associated with area dA, this will be d phi, and that will be given by E dot dA. Now to calculate this flux with the complete area, what we'll do, we'll integrate this expression d phi and this E dot dA. Because here area is the factor with respect to which this is being integrated. So this is a surface integration. Surface integration means double integration. It will be integrated lengthwise and breadthwise both. Value of electric flux can be positive, negative or zero also. How? Phi is E dot A or EA cos theta. So if we have theta is equal to 0 degree, that is electric field lines are here and the area vector is also in the same direction, then theta will be 0. In this case, because your surface will be placed like this, so obviously maximum electric field lines will pass through it and the flux associated with this surface will be maximum. So phi maximum, this is equal to E into A. When we take theta equals to 90 degree, 90 degree means area vector and electric field lines have angle 90 degree. So in this case, your area is placed in this manner. So area vector and electric field, they have 90 degrees. So we can see that electric field lines are not crossing the surface, they are along the surface. So in this case, flux will be 0. Here, flux will be 0. Third case, if I take theta as say 180 degree, means our electric field lines are in this direction and surface is placed in opposite direction like this, that the area vector is in the opposite direction, then your angle will be 180 degree and phi will be negative. Now we'll understand that what is the role of Gauss theorem in the calculation of electric flux. We know that for any arbitrary surface, electric flux is calculated by the formula E dot dA, that is surface integration of electric field with area. Now surface integration means this expression has to be integrated twice. Surface means its length into breadth. So we'll put limits in 2 times, one for length, one for breadth. So this is a very tedious method to calculate electric flux. So to ease this expression, to ease out the way of calculating electric flux, Gauss gave a theorem with the help of which we can very easily calculate electric flux. Now what is Gauss theorem? Gauss theorem says that if I have a charge, if there is a charge and it is enclosed in a surface, there is a surface which is enclosing this charge. Suppose this charge is Q. It can be positive or negative, both charges. So there is a surface whose surface area is, suppose A, and it encloses volume V. This volume of the whole complete surface is V, and here inside this surface there is vacuum. If charge is placed, obviously electric field lines will move from here. They will emerge from it if this is a positive charge. Then Gauss theorem says that the surface integral of electrostatic field E, this field E, that is this expression, surface integral of electric field E produced by the surface, this closed surface which encloses a volume V in vacuum, that is the total flux which is coming out of this surface, is equal to 1 upon epsilon naught times the total charge enclosed in the surface. Means if I have to calculate electric flux which is linked with this surface, say A, which has a volume V and plus Q charge is enclosed in it, then one method of calculating this flux is that we first calculate E dot dA, dot product of electric field with this small portion of area, and then we integrate it twice, that is we take surface integral of this, and then we'll get the value of electric flux. Gauss said that the same thing can be calculated, by a simple expression which is 1 upon epsilon naught times the total charge enclosed in the surface. Here epsilon naught is the permittivity of free space or vacuum, because we have taken vacuum here, so we'll place epsilon naught. So he said that this can be done in a very simple manner by taking this expression. The surface that we have taken here to calculate electric flux, this surface is called Gaussian surface. Now Gaussian surface, how do we define it? Gaussian surface is the surface chosen to calculate the surface integral or to find the electric flux. This surface is of our choice. I mean, we can always choose the shape or size of this surface according to our convenience. We'll choose such a surface so that we can calculate this flux easily. Now, how do we prove Gauss theorem? We can take a point charge and then we can prove it. In proof, what we assume, take a positive charge, point charge at a place. And around it, we consider a surface that is Gaussian surface of spherical shape. This is a spherical shape, radius R, this position is O. Here is a plus Q charge and around it we have taken a surface, Gaussian surface of spherical shape. Now here at this position, because from this plus Q charge, electric field lines are emerging out, they are coming out in all direction. So we are taking this direction. Here I take a small portion, small area of this sphere. Say this is ds. And because it is in this portion, so its area vector will also be in the same direction. It is ds. Now, because of this plus q charge, if I write the expression of electric field at this position, say this is P, electric field at P due to charge plus Q. So this will be 1 upon 4 pi epsilon naught Q upon R square. Now the flux linked with the surface, that is ds. This surface, we'll take it as d phi. This is equal to E dot ds. E ds cos theta, we can see here theta is 0 because electric field and area vector, they both are in same direction. On sphere, if I take the area vector on this area, obviously it will be perpendicular, in perpendicular direction, and electric field is also perpendicular to the surface, so they both will have 0 angle. This is E ds. Now total flux linked with the spherical Gaussian surface for that we'll integrate this d phi, and that is equal to this EDS will also be integrated as the spherical body, this body. For this, electric field will be same at all points, so E is constant for this surface, so we can write it as phi is equal to E outside the integration sign, this is ds. So ds is the total area of spherical body. I know its value is E is 1 upon 4 pi epsilon naught Q upon R square, and area for this spherical surface will be 4 pi R square. This 4 pi R square cancelled, and we get Q upon epsilon naught. So phi here for the spherical Gaussian surface, we have proved that it is equal to Q upon epsilon naught. If I take shape of this Gaussian surface other than spherical body, then also we can prove that the phi will be Q upon epsilon naught. But because spherical surface is the convenient surface, so we have chosen this as a Gaussian surface to prove Gauss theorem. If inside this surface there is vacuum, we write Q upon epsilon naught. But if this area is filled with some medium, suppose we are filling it with a medium, say epsilon, then flux will be equal to Q upon epsilon, and this epsilon will be written as K into epsilon naught. Here K is dielectric constant of that medium. If there is no net charge enclosed in this Gaussian surface, suppose here charge is not enclosed, Q is 0. In that case, electric flux linked with the surface will be 0 because there is no net charge. In case of electric dipole, I know that electric dipole has minus q charge and plus q charge, equal and opposite charges. So if they are enclosed within a surface, then also net charge will be 0. So for electric dipole, electric flux linked with the surface is also 0. Now when we say that here we have to take enclosed charge, so which charge is considered as enclosed charge? Suppose I have placed a charge Q1 here, Q2 here, Q3 here, Q4 here. Q1 is at center, Q2 is close to the boundary, Q3 on the boundary, and Q4 is outside the boundary. Now enclosed charges will be Q1 and Q2. That means we'll consider only Q1 and Q2 as enclosed charges because they are inside the surface. Q3, which is on boundary, will not be considered as it will not be considered as enclosed charge. Then Q4, because it is already outside, so this is also not enclosed charge. So if I have to write phi here, so it will be Q1 plus Q2 upon epsilon naught. Another fact that the flux, what is linked with the surface, does not depend upon the shape and size of this Gaussian surface. If I take rectangular surface in place of this spherical surface, then also if the charges are same, the flux will remain same. I take the boundary, I take the different boundary. Suppose I don't take this, I take this boundary, but my charge enclosed should remain same. For this sphere also Q1 and Q2 are enclosed. For this sphere also Q1 and Q2 are enclosed. So if I change the shape, charges enclosed are same, then flux will remain same. Now, what is the use of Gauss theorem? How do we apply it in various areas? So first application of Gauss law is that we can get an expression of electric field of a long straight wire which is charged and it is of infinite length. Because it's a long wire, infinite length wire, so obviously we cannot use the expression of electric field for point charge because a straight line, straight wire is not a point charge, so we cannot use all those Coulombian expressions in this case. So here we use Gauss theorem to get the electric field of the straight line wire. Electric field due to straight infinite charged wire. Now, suppose we have a wire. I'm taking a small portion of this wire, but this is infinite length wire and this is say positively charged. This charge is uniformly distributed over the length of wire. Here, what is the total charge present on this wire? We cannot guess. So we define linear charge density. We take linear charge density. Denoted by lambda. This is equal to charge per unit length of the wire. So we know that how much charge is present on unit length of the wire. Now how to find the electric field due to this wire on a point say P which is at distance R from this wire. I cannot use E is equal to 1 upon 4 pi epsilon naught Q upon R square because this is not a point charge. So what we'll do, we will take a surface here, cylindrical surface of radius R and length L. What I'm doing, I'm taking a surface which is Gaussian surface actually of radius R and length L. This wire is the axis of the cylinder. So the cylindrical surfaces are Gaussian surface. Now, in this Gaussian surface, we have three parts of the surface. This is one. This curved surface is 2. and this surface is 3. So area vector of first surface will be directed here. For curved surface, if I see at this point of curved surface, electric field will be, area vector will be upward. For this surface, it will be in left side. So these are the area vectors. Now if I see the electric field for these 3 parts of the surface, on this cross section, first surface, because positive charge is going along this direction, obviously electric field due to positive charge is always away from it. So for this surface, electric field will be directed in this direction. Same for surface 3. This side and here downside. And this curved surface will also have electric field. It will be like if I take a circle, then on all the points on circumference, it will be perpendicular to all the points. Now what will I do? I'll find electric flux. We'll apply Gauss theorem for that. Gauss theorem says that E dot dA, that is equal to phi. This will be equal to E dot dA for surface 1 plus E dot dA for surface 2 plus E dot dA for surface 3 should be equal to Q upon epsilon naught. Now if in the diagram I see, look at the diagram. For surface 1, E and this area vector are perpendicular. So for this flux will be 0. For surface 3 also it will be 0. For surface 2, because E and dA are in same direction, angle is 0 degree. So we'll place this value here in the expression. For 1 and 3 it is 0. So this is 0 plus second surface will be equal to E dA plus 0 equals to Q upon epsilon naught. Now here E will come out of the integration sign because on circumference, on the curved surface of cylindrical body, it will be constant. E, this is area of cylinder, that is curved surface of cylinder. Here Q can be written as lambda into L upon epsilon naught. Area of curved surface will be, for cylinder it is 2 pi r L, that is equal to lambda L upon epsilon naught. We can cancel out L and here we get electric field lambda upon 2 pi epsilon naught r. So this is the electric field of a straight infinite charged wire when we cannot apply Coulomb's formula or Coulomb's law on that. Then we do it with the help of Gauss theorem.